this country and around the world. Now, what we've decided to do is something a little bit different. Because many of you may have seen his television show or read his books, what we thought, in order to provide, in some sense, a break from the continuous lecture format, is we're going to have a dialogue, and we're going to talk together about some of the issues of physics and science education and communication, and then we'll open up to questions from the audience. So I'm very proud and pleased to welcome Brian Greene to the stage here today. Brian. Thanks, Brian. This will be an interesting experiment to see how it goes. I thought we'd begin by asking, in some sense, what made you become a physicist? What got you excited? And why did you choose the area of physics that you ultimately decided to work in?
You know, I've never thought about that before. No, it's a great question. I think, like many of us, it's probably true for you too. And I've never spoken to our community, but I started in mathematics. You know, as a little kid, my dad would set me these little problems, and I was just amazed at how, with just a few little tools of knowledge, you could actually calculate things. You know, multiply numbers and do calculations that perhaps no one had done before. No one had done before because they weren't interesting, but it was still, you know, fun for a kid to do. And then later on, I must have been 12 or 13 or 14, you know, I went through the kind of thing that most everyone goes through. Why am I here? What's it all about? All that kind of, those interesting questions, those deep questions. And it just occurred to me that if people are still asking those questions, there must not really be some fundamental answer. So maybe the best you could do is try to understand the question. And when I learned that math could help you learn about those questions, you know, how the universe began, even what it means to ask that question, I was pretty hooked.
So that's interesting. You came in from math. I think that's.
Yeah.
What about your parents? Did they were they surprised, disappointed? My mother wanted me to be a doctor, for example, and she was very disappointed when I became a physicist.
Are you Jewish?
Yeah.
Yeah, me too.
Yeah.
So, yeah, I've had exactly the same experience. In fact, I still have that experience.
Yeah, well, I got a job at Harvard. My mother said, I remember my first job at Harvard was a nice job, and my mother said, it's still not too late.
Yeah, absolutely. No, my dad was a composer.
Oh, okay.
And as with many composers, very hard to make a living. So he supported the family by playing bass fiddle at you know, weddings and bar mitzvahs and things like that.
Really?
And he was a vocal coach as well, a singer. My mom was a secretary for a veterinarian, so it was not a very traditionally academic household.
What about, I know one of the reasons I write books, and I wonder if it's a reason for you. What about, did you read books by scientists? For me, that was very inspirational. Did that affect you at all?
It did, a little bit later on. You know, I somehow didn't know about this whole area of science books without the technical details until I was at least sort of 13 or 14. Huh. But it was really two books. It was a Carl Sagan, you know, Cosmos, but it was also The Ascent of Man,
yeah,
Bronowski. And those two really just stuck with me as a very potent way of communicating information without having to go to a course, without having to study it. And so that certainly was with me all through my education as something I valued.
Okay, so why then physics and not mathematics, although?
Well, it was really just a recognition that math, you set yourself the problems, whereas in physics, nature sets you the problems. So it felt like you had the capacity to, in the most grandiose language, sort of touch eternity. You know, if you were lucky, if you were among the lucky few whose work actually was relevant to the world, you'd be revealing something that could stand the test of time. And that, to me, just had this pull.
Okay, now we got to physics, particle physics, and ultimately string theory. What about that?
Well, when I was in college, I had a real obsession with gravity. And I'm hesitating.
You know, I think that's true of pretty well all students, actually.
Yeah. Well, I'm hesitating a little bit because it's a little bit odd. I mean, you know, many of you may be familiar too, but you know well Steven Weinberg's book,
yeah,
you know, Gravitation and Cosmology, Principles and Applications of General Theory of Relativity. And, you know, it's this, and I bought that book, I didn't understand it at all. I think it was a freshman or sophomore, but I used to walk around with carrying
Did
it,
it help you meet women? Or
caressing it, sort of. I just wanted to know what was inside that book. And then when I began to understand it a little bit and learn that there was this big issue, how do you incorporate quantum physics into gravity, I became very, very caught up with that notion and basically stayed in that area ever since.
Now, I'm trying to remember, because I think I was at Harvard when you were still a student there. But when string theory already, I mean, you were interested in gravity, but string theory hadn't yet taken off.
It was an interesting timing. So I graduated in '84 and went to Oxford. And in the fall of that year, fall of '84 was really the big breakthrough year. So at Oxford, there was this sense at first, when I first got there, I have to say, the older students said, turn back.
Yeah, quantum gravity, before string theory, it was the dead end. All these good students want to do it, and you never heard their name again.
And moreover, there were even particle physics students who said, this field is drying up. And it was a real kind of depressing couple of months hearing the older students with that perspective. But then, you know, this big shot out of the blue, these discoveries in string theory just changed everything.
Yeah, maybe now it's time to talk a little science. So maybe want to fill in a little bit about what happened. What was the major breakthrough that made string theory of interest to people, and then we can go on.
I mean, maybe 30 seconds background on string theory itself.
Yeah.
So, as many of you may be familiar.
Well, I think
I guess the audience already knows all the string theory.
Yeah, that's right.
I forgot where I was.
Yeah, that's right. This is ASU. Now, come on.
Yeah.
Okay.
Anybody want a little bit of background string? Okay, good. So, you know, in the 20th century, the two big developments that we all study intently were Einstein's breakthrough in understanding gravity, the general theory of relativity, and the other breakthrough in a field called quantum physics that focuses on the completely other realm of the spectrum in terms of size, the small things. General relativity big, quantum mechanics small. The weird thing was when you tried to put them together, the math just wouldn't work. So this was a big puzzle. And string theory is an approach that tries to resolve that puzzle, put gravity and quantum mechanics together into one theoretical package. And the only feature of the theory that really I think is worth keeping in mind, because it's very visual, string theory suggests a new way of thinking about the ultimate constituents of matter. You know, molecules, atoms, subatomic particles, we view them as little tiny dots traditionally. String theory suggests, and I underscore suggests, these are not proven ideas, but inside of these little dots, string theory suggests you'd find something else, a little tiny filament, a little tiny string-like entity that vibrates. And it's called string theory. It looks like a little piece of string. And the idea is that the different vibrational patterns of this little tiny filament is what gives rise to the different particles. The string vibrates one way, it looks like a quark. It vibrates a different way, it looks like a photon. So all the particles are the different musical notes, if you don't mind that metaphor, that the little tiny strings can play. That's the basic idea.
And there's another important component of it, a very important component of it, is that string theory to be mathematically consistent requires extra dimensions. Maybe it's very important. The strings vibrate not just in the dimensions we see, but in principle, extra dimensions, which is a major challenge of string theory because most of us in the room usually are used to just 4 or 3, in fact, and we rarely throw a baseball and have it disappear into an extra dimension. So maybe you want to talk about that a little bit.
That's absolutely right. That is one of the strangest implications of the theory. So when I said that you put general relativity and quantum mechanics together in one mathematical package, what I really should have said is there's a mathematical framework that when you study it, you find that it fails if there are only 3 dimensions of space. That is, if you only have left, right, back, forth, and up, down, these 3 dimensions that we all know about, the math breaks. And some people said, well, let's look at it even more intently. What happens if there are 4 dimensions of space? It still breaks. 5, 6, 7, 8 still breaks. But you get to a total of 10 space-time dimensions, and all of a sudden, the math falls into place. So that's where this strange idea that there may be more dimensions of space than the ones that we know about comes from. And frankly, I and many others have spent the most of my career trying to figure out where those extra dimensions are, what their features look like, and perhaps what implications they might have for physics that we can see in the world around us.
Now, in fact, of course, one of the big it's interesting. When this idea first came up, the idea of extra dimensions, early in the century, in last century, it was developed independently by a mathematician and a physicist. And the mathematician said, well, you know, you can have these consistent extra dimensions that do interesting things. But the physicist rightly said, okay, if they are there, how come we don't see them? Yep. And the original idea was that they were extremely small. So they're so small you can't see them. Maybe you want to elaborate on that.
Sure. So the gentleman you're referring to, Krauss, way back in 1919, was basically studying Einstein's general theory of relativity, which had been so successful at describing the force of gravity. And the language that Einstein used was unfamiliar. He used the language of curved space, in fact, curved space-time, as the medium for mediating the force of gravity. So right now, according to Einstein, I'm sort of feeling myself being pulled down because my body wants to slide down an indentation in the curved space-time that the Earth creates. So it's an unfamiliar idea, but a powerful one. Kaluza looked at it and said, well, that's interesting. What if the other forces of nature, namely the electromagnetic force, also can be described in that language of curved space? But the problem was Einstein had used up all of the known dimensions of space. So Kaluza said maybe there's another dimension of space, and maybe ripples and curves in that would describe the electromagnetic force. And he did the math, and lo and behold, the equation for electricity and magnetism popped out by the simple assumption of one more dimension of space. But then the question is, where is it?
And, you know, I think it is interesting, don't you think, though, that it's sort of an interesting differentiation between mathematics and physics, that he was just perfectly happy with that and didn't bother to ask the next question. And it was Klein, the physicist, who then asked it.
And it was Einstein, too.
Yeah,
you know,
that's true.
so, I mean, at least as the story goes, Kaluza sends that paper to
right.
Einstein, and Einstein at first is very excited about this because he himself was fixated on unifying the description of all forces, not just gravity. So he loved this idea that by having one more dimension of space, you could put together electricity, magnetism, and gravity in one framework. Wow, that was just what he was looking for. But then, like you say, he said, hold on, this is crazy. We only have 3 dimensions of space, so this can't possibly be the right way to go. He thinks about it for another year or two, holding up publication of this paper, much to the consternation of Kaluza.
Yeah.
And finally, Einstein says, yeah, maybe this is possible. But it was Oscar Klein who really then came along and said, well, here's how to think about it. There can be more dimensions of space as long as they're really small. The ones we know about are big. We can really see all these dimensions because they're large. But imagine there's a tiny, curled up, crumpled up dimension that's so small that we don't see it. And in this particular case, they imagine if you had a little tiny additional circular dimension all around us. The image that I like to use is, imagine you're looking at a carpet from far away. It looks flat. But then you put your eye right down on it, and you see these little tiny loops, these little pieces of thread called the pile, I guess. So you see these little tiny circular pieces attached to the carpet, extra dimensions curled up. You don't see them from far away. The idea was maybe that's true of our universe. Extra curled up dimensions all around us, so small that we don't see them.
Okay, so that explains why we don't see them. But of course, there it is over there.
Thank you.
The job of physics is not to explain why we don't see things, of course, but to test the ideas and explain how we can see them, or at least how we can tell that they might exist. Well, maybe you should talk a little bit about the challenge. And one of the reasons that string theory is at this point has not yet sort of made touch with experiments. So maybe you should talk about that a little bit.
Yes, and I think, you know, jumping off from the historical line is not a bad way to go, because after Kaluza and Klein suggested this idea of an extra dimension, they did try to see if it could make contact with experiment, and they found that, for instance, it was very hard, almost impossible, to get the electron, a known particle of matter. They couldn't incorporate it successfully into the theory. And that was largely why this idea was ultimately dropped by the 1940s. Then string theory came along in the 80s, and it didn't just allow for extra dimensions. It required extra dimensions.
Actually, I think it is interesting to point out that it really came along the sort of, or at least the
60s.
the
Yep.
60s,
Yep.
where it was first used to try and explain another
Good
force
point.
of
Yep.
nature. And actually, and maybe it's an interesting question. Neither you or I were practicing physicists then, but at that time, I don't think you were anyway. At that time,
Oh, speak for yourself.
Yeah, that's right. At that time, it wasn't 10 dimensions; it was 26.
Yeah.
And I was amazed when I sort of gone back and looked at that stuff to think that the questions were so desperate that people would be willing to accept not 6 or 7 extra dimensions, but 22 extra dimensions. And maybe you want to talk a little bit about why it would be that physicists would sort of be willing to make that incredible leap.
Yes, so you're right. The earliest version of string theory, I should say, did require 22 extra dimensions for this total of 26 if you include time. And I think the reason people were willing to take it seriously is twofold. One, there had been so many attempts to put gravity and quantum mechanics together, and they all failed. They all just broke down. So when an approach came along which seemed to work but required something weird, and yet that weirdness was something that had already been contemplated in one form or another decades earlier, in some sense people said, well, you know, whether it's 1 extra dimension or 2 or 5 or 22, it's the idea, getting over the notion that this is all that there is. Once you allow for more dimensions, the actual number doesn't seem to really sway you much one way or another.
Yeah, I mean, if you got a bunch of X. But I was actually thinking of going back. I think it's interesting to me that even in the 1960s, where they weren't talking about gravity, they were talking about another force which wasn't so profound at that time. There was just a big problem. Accelerators kept coming up with new particles, and there were particles everywhere, and the zoo was growing, and it appeared there was no order. That when people came up with an idea that they thought might provide order, they were willing to at least explore this idea.
That's exactly right.
And I think it represents the fact that it's not, and we'll ask you about, one of the things I want to ask you is if you really think there are those extra dimensions in a moment, but the idea of exploring them and using that hypothesis and seeing where it goes without becoming religiously devoted to it, I think is interesting, is that you're willing to try anything to see if it works. And in the case of the 1980s, what they discovered, well, they'd had the right solution, but asked the wrong question. At least they hoped they had. So
that's exactly right. So the earlier version of string theory was not trying to resolve this incompatibility between quantum mechanics and gravity. Strangely enough, the earlier version of string theory, as you say, was trying to describe data that was coming out of accelerators worldwide that were finding this whole slew of particles, the zoo that you mentioned a moment ago, this whole slew of particles without any order. And string theory, in its earlier version, seemed to supply an order. All these particles now being thought of as different vibrations of the string gave an organizing principle for thinking about this wealth of data. The problem was there was one pesky particle that came out of the mathematics of string theory that was not found in the accelerators. It was a particle that people a few years later recognized as just the kind of particle that you would need if this was a theory embracing gravity, a particle known as a graviton. So people said, let's take a big step back, reevaluate this theory, not just think of it as a theory that describes the particles, and footnote, another theory had come along which did a better job at that, quantum chromodynamics.
And two of the people who won the Nobel Prize for it are at this at our meeting right now, in fact.
So people said, let's not try to answer that question, which that other theory does better anyway. Let's take this vice of this graviton particle, make it a virtue. Think of this now as a theory uniting gravity and quantum mechanics.
Actually, it's interesting you talked about this vice and virtue. It may not be a secret to many of you that Brian and I have appeared on stage a number of times in a more combative format, a debating string theory, which we're not going to do today because I won the other ones. But I want you'll get your shot. No, but anyway, why don't you talk about this vice to virtue thing? I mean, in some sense, the difference between the string theory of the 60s and the 80s and since that time is a huge leap. That string theory, in its modern form of trying to attack this fundamental problem of quantum mechanics and gravity, and let me make it clear, I'll say it in public, it's the best bet at this point. Okay, I'll come back to other things about it, but
technical crew, can you just cut out that snippet and send it to me? Just that little piece right there.
No, we're in a complete agreement. But it's completely different in the sense that it's really right now guided by mathematics for the most part.
Yeah.
And so I wonder whether you want to comment on this sort of role of aesthetics and mathematics versus experiment, because it's a new leap in a sense. So
It is a new leap in some ways, but I think you would agree that if we look back at the history of physics, say in the 20th century, there are many moments where mathematics was playing a pivotal role in guiding the next step. Now, what was certainly the case, for instance, in quantum mechanics, it was much more an interplay between data and mathematics because we were describing a realm that we could probe experimentally.
Yeah.
So we had the shining light of experimental data to help guide the math, this wonderful back and forth between the theory and the experiment. You know, Einstein, though, was largely guided by just this powerful intuition and mathematics. I mean, the idea that gravity is associated with curved space-time, I don't know about you, but I've never gotten over the awe that I initially felt that he came up with this idea. It's just how in the world did he come up with this? And it was just this powerful intuition that was working within the confines of mathematics.
Although I mean, he did have pictorial experiments. He did have those Gedanken experiments, the idea that light, think of an elevator accelerating. He tended to think pictorially, and ultimately he forced himself to learn the mathematics he needed and was almost beaten by a mathematician in his own game.
That's right. But I think it's pretty clear that it was not just this unbridled pictorial sense, this unbridled creativity. It was working within the context of a mathematical framework that really allowed him to go forward. And I think the difference today is we're in realms that are beyond current abilities to probe experimentally, or maybe not. We'll see at the Large Hadron Collider. There's a possibility. So we have to be guided yet further by mathematics. And could mathematics completely lead us astray? Yes, it's certainly possible. I don't think so, but it's possible.
Why don't you think so?
Well, it's just the experience that we've had. And it's also this deep-seated sense that mathematics is this language. It's almost tailor-made to describing the universe. I mean, we have, as you say, I don't know if they're in the audience right now, but they'll be in the program later on. There are folks in our community who've been rightly lauded because they came up with theoretical ideas, took them seriously, that yielded predictions for particles that had never before been seen, and then people looked for those particles and found them. I mean, it's kind of breathtaking that you do this calculation and these symbols on a piece of paper that you got to by following some well-defined rules, a language, if you will, yields a new insight, and it's confirmed.
In fact, maybe that's something we should spend a minute on, because it actually in some ways relates to the talks we heard earlier and came up at our meeting. It's more than breathtaking. It's actually humbling and intimidating. The notion, I know Steve Weinberg, who was here earlier, has said that the idea that when you're sitting in your room working on a piece of paper, that nature actually obeys the laws, that nature, not listens, but obeys what you're writing down. It is almost incomprehensible when you're actually working on it. It's thrilling but intimidating at the same time. And I think one often sees, it's surprising to me that physicists are seem to be more willing to sort of throw caution to the wind in that regard. We talked about the fact that, for example, one of the reasons evolution isn't more lauded than it should be. Evolution is one of the most remarkable scientific ideas that's ever come up, and certainly Darwin. Einstein's gotten great press, but Darwin did more, actually, in my opinion. But one of the things is that he didn't actually make predictions. It's interesting. He didn't say, hey, there's gaps in the fossil record. We should look there, and it's a test idea. When you find it, you could vindicate it. But in physics, we tend to say, hey, this theory will fall apart if you don't find X or Y.
Yes.
But at the same time, well, let's ask, what would fall apart? I mean, this is the problem with string theory in some sense. Right now, we don't have something that would fall apart if you didn't find X or Y.
That's right. And framing it that way and using evolution as a backdrop, I think, is quite reasonable because, in a way, we're not using the right language, right? I mean, for evolution, as people were describing earlier, this notion of it just being a theory is sometimes used as a strange and really unjustifiable weapon against the theory because when we, as scientists, use the word theory, we mean something very specific. You know, the best available explanation for the data that we have at hand, and we're most happy with a theory when it makes predictions that are confirm or confirmable. And string theory does not meet those criteria. So in more precise language, you know, string theory should be string hypothesis. You know, David Krauss discussed it as a string framework. I use the language string hypothesis.
No, I agree.
know.
I think I've always said it's unfair to evolution for string theory to be called theory.
And that I'd have to agree with you, actually. I'd have to agree with you.
Could we get that?
You know, but there's, you know, it's just historical precedent that this is the language that we've fallen into. But back to your question in particular, we understand a lot about, let me just use the language, string theory, and we have, in my opinion, achieved things in that structure that when, for instance, I was a graduate student starting to work in this, I never thought that we'd get this far in the length of time that we have been working on it. But we've not yet gotten to the point where we can start with the equations and come up with some definitive prediction such that if it is not confirmed, we give the theory up. I mean, vaguely we can come up with things like that, but they're so universal that it wouldn't really rule out string theory. It would almost rule out all physics if it weren't found. And that's not a happy place to be. And, you know, it's funny how, you know, not with you, but I have encountered some people who almost interpret that as a situation that string theorists are happy with because it's some kind of, I don't know, job security or something like that. You know, people don't understand the tenure system or something like that. But the bottom line is, I certainly feel, and I'm sure all my colleagues agree, that if string theory is wrong, I really want to know right now. I'd like to know 10 years ago. Because I'm not in this game to prove one particular theory right or wrong. I'm in the game because I hope that I'm part of a generation that takes us one step further, regardless of what that step happens to be. So we're working very hard to try to come up with things that we might test. And there are some circumstantial things that we could talk about that might happen at the Large Hadron Collider.
We'll get there probably.
But you know, we cannot do what you asked, namely say, this falls apart unless you find that.
Now, in fact, actually, you know, he hit an important point. People tend to think scientists are wedded to theories. And in fact, scientists most often want to be wrong. More importantly, they want their colleagues to be wrong. And, and because it gives you a chance to discover something new. And so in a sense, we want to be surprised by nature. And in fact, it's fair to say that you know, there's an interplay between theory and experiment, and we've tried to talk about that a little bit. And sometimes one leads the other. And if string theory has any validity, it'd certainly be an example of that. Usually, it's the other way around. Usually, experiment surprises us and derives us. And so the other thing I wanted you to elaborate on is that there's a problem that right now we haven't yet made contact with reality. But there also is the mathematics of string theory have gotten, you could either say more complex or more fascinating. And in fact, the theory has become much different. In fact, strings may not be the most, it may be not only may theory may not be the right word, strings may not be the right word. Maybe you want to talk a little bit about that.
Yeah, so one of the big breakthroughs in the theoretical development of string theory happened in the mid-1990s, where techniques were developed to go beyond the approximate methods that had almost universally been used in calculations up to that point. And when people employed these more exact techniques, they were able to reveal aspects of the theory that were completely hidden previously. And one of the things that was revealed is that the description I gave in terms of the fundamental ingredients being these filaments, these string-like entities, is incomplete. The theory seems to also have within it objects that are two-dimensional, looking more like membranes, or three-dimensional. We call them three-branes, generalization of membrane, four-dimensional entities, and so forth. So there's kind of a democracy, if you will, of higher dimensional shapes that play a role in the theory. Strings were discovered first because they're the easiest part mathematically to reveal. But if we had the exact techniques from the get-go, we probably would not have singled out strings as the one entity by which we named the structure. So yes, that's one of the big developments, and that has suggested a whole nother way of thinking about the theory.